Okay, so we will do combinatorics, graph theory, number theory, and abstract algebra. And above all, we will define, or we will define it not very properly, but through examples, we will define what proofs are and how do you prove things, right? About especially mathematical statements. How do you formalize and then how do you prove? Okay, so how to give a proof? So to define it very formally, you have to do it in a course on logic. So we will not do that very formally here, but we will just take an informal approach to proofs. And yeah, in this course. So which means that, I mean, especially for your purposes of your writing and your exam, what it means is that you have to start with the proof idea. You have to clearly state what the proof idea is that you are going to take. And similarly, in your algorithms or programming course, you have to state what is the proof of your algorithm and what is the basic idea of your algorithm, of your proof, and then you give the proof. Okay, and the proof should not go into extreme level of detail. That is not the expectation, because otherwise we cannot read it. It should be readable. It should have enough details, but not everything to the last bit, right? So you have to give the details, but also it has to be made readable, and the only way to do that is in the beginning you state what your basic idea is, and then you go to some level of detail, and hopefully you will get full marks for that. So we will exhibit it through examples. And ideas. Okay, so the very first theorem is, which I am sure all of you have read at some point. So the theorem 1 of this course. It was shown by somebody, we don't know the name, but it is in Euclid's books. Okay, so around 2500 years ago it was written down, but maybe probably proved much before. So it says that there exists a prime greater than n. For all n, there exists a prime greater than n. Okay, in this class we will define these quantifiers more carefully, but for now it is just a shortcut for English. So we are saying the statement is that for all integers, for all natural numbers n, you can find a prime number which is bigger than that bound, and a number is called prime if it is an integer, it's a positive integer, and it's not divisible by anything except the trivial, which is 1 n itself, right? So like 2, 3, 5, but not 4. So the question is, how many such numbers are there? Are they finite or infinite? And this theorem is saying that they are infinite, right? Because for any bound, you can go above that. So how do you prove this? What is the proof idea? Yeah, so without defining what a proof by contradiction is, we will just give the proof so that you learn both the things, how a proof proceeds and what exactly is this proof by contradiction. So you assume that there is a number n such that there is no prime above it. So assume that there is no prime above some n. Okay, so above some bound which we are calling n, we could have called it x or a or whatever. The alphabet is not important, but what is important and would have been quite critical in those years is that you are actually assuming something opposite to what you want to show, right? So you want to show that there is always a prime, but here you are assuming that suppose that there is not. And then what happens? So obviously, you don't have any foresight at this point, what could happen. But as you can see, there will be a sequence of simple deductions which will ultimately lead to something absurd. Okay, it will show opposite of what you have assumed. And how, so what is the first step? What do you do? After assuming that there is no prime beyond this number n, this unknown number n, what happens? Sorry? Right, but what is the expression? So goal is clear, but yeah, so the expression is you look at n factorial. Or you could have just taken product of all the primes below n. So basically all the primes that you know in the universe after the assumption, they are finitely many, right? They are all below n or below. So you take the product of those, which, or simply you can just look at product of 1, 2, 3, n, which is n factorial. So let's just look at that number. That's well defined. Okay, so this notation will mean we are defining, on the left side we are defining m. So now this alphabet, this letter m now denotes n factorial plus 1, where n was unknown, so m is also unknown, but you are assuming that both of them exist. Okay, so the assumption in this proof is that n exists, hence m exists. And what is the property of m? None of the known primes can divide it, right? Why is that? Give a short proof for it. Sorry? Yeah, so let's look at some explicit number like 2. 2 will divide n factorial. So 2 cannot divide multiple of 2 plus 1, right? Similarly, you can do it for 3, and for any prime you can show, in fact for any divisor of n factorial you can show that the plus 1 stops, basically if you divide by the divisor you will get remainder 1. Okay, this is by construction. So that's the next step. For some people it may be obvious, and for others it may need another line of proof. So depending on where you are, you can fill the details accordingly. But you can safely conclude then that none of the primes divide m. So not below, but I think less than equal to n. None of the primes up to n can divide m. In fact, you also know the remainder. If you divide m by any of the known primes, the remainder is 1. Right? So then clearly there is no division possible. Which means what? What should be the next conclusion? Yeah, which means that, by the definition of prime numbers, right? So now we are invoking the definition of prime. You can deduce that m is prime. And what next? M is clearly greater than n, right? So you have found a prime which is bigger than that unknown n, which means that, so m is prime and obviously by definition it's greater than n, which means that it's a contradiction. Okay, so I'll use this notation for contradiction. It basically depicts that lightning has struck and math is destroyed. Okay, but that cannot happen. In math is believed to be consistent. So if you reach a contradiction, then it only means that you made a wrong assumption, because all the intermediate steps were correct. So it means that your starting point was wrong, which means that there has to be a prime above every known n. Any n you pick, there is a prime above it. Okay, so this means that the theorem is true. Okay, so that's the end of the proof. Any questions about this? You have a question? Because see, if m is not prime, then there has to be a factor which is prime. Here again, some proof is required, but once you define factors, then you can also show that any factor, any divisor can be further factored, and you continue this till you reach a prime number, right? So if m is not prime, then ultimately there is some prime which divides m. But what is the set of primes? The set of primes is actually a subset of 1 to n. That's the assumption. That was the first line. So the primes, basically here what you are assuming, that the set of primes is a subset of 1 to n. Right? So if m is not prime, then there is some prime factor. The prime factor will then be sitting in the set P, fancy P, and then it cannot divide m. That again is contradiction. So the only possibility is, whichever way you go, you get a contradiction to some assumption. Is that clear? Any other question? Divide, yeah, that's a typo. No, as I just said, the assumption is that the set of primes P is only that. These are all the primes. So any prime number that divides P, M is sitting in that set, and that set is absorbed in n factorial. So any such prime, any prime factor of m, you get this contradiction that it has to divide m, but it also divides n factorial. But how can a number divide both n factorial and n factorial plus 1? Right, so that's a different contradiction. So whichever path you take, there is a contradiction, and that's the proof. So it's a tricky proof. And since it ends in a contradiction, we call this technique proof by contradiction. And this is the first example in all of math for this technique. Okay? Fine. So this also means obviously that there are infinitely many primes, but it doesn't tell you how many primes are there up to n, 1 to n, how many primes are there. The densities it doesn't give. That way, after mid-sem, we'll give a short proof about the density of primes. So they are actually quite dense. Almost any number you pick, it turns out to be prime. Okay, they are found aplenty. So that's a correct proof. Now let me give you an incorrect proof, and then you find a mistake. So okay, this also shows that the set of primes is infinite. Okay, this is what we have shown. Now let's look at another proof example. So recall the infinite geometric sum formula that we have learned for JE. Okay, so let's apply it here. So you have an expression, or let's call it sum. You have the sum like this, it goes 1 plus x square, so on till x to the infinity, forwards and also backwards. Okay, so it's a sum which goes both backwards and forwards, x square, and 1 by x square, and so on. So how do you sum it? Being good JE students, you will very quickly see that the right side is 1 over 1 minus x, right? And what is the left side? X inverse by 1 minus x inverse. So this is 1 over x minus 1 and 1 over 1 minus x, which is 0. Right? So is that a proof? Why not? It seems to fit all your formulas. Yeah, so I did not specify what x is, right? X can be 2 or x can be 1 by 2. So if x is 2, then the forward direction is false, because that formula for infinite geometric sum requires a fraction, x to be a fraction. And if x is half, then the left hand side is false, but since we are applying both of them simultaneously, only possibility could have been x equal to 1, but then at that point the series, as you see, diverges, right? So there also you cannot apply the formula in both the cases. So in all the cases this formula is actually wrong. You can never find an x for which this sum is 0. Right, but this calculation used to happen in 1700s, 1800s, like even Euler saw a manuscript and he found this error, I guess. So yeah, when these things are not formalized, then you tend to make mistakes based on intuition. So the right answer is that such things are not proofs. As x needs to be x or 1 by x, or let me say as geometric sum application is has opposite assumptions. Right, so you have to be careful when you are applying geometric sum, because if you apply it on the left side, then you have already fixed 1 by x to be less than 1 or x to be greater than 1, and then you cannot apply it again on the right side. Okay, you can only apply it on the left side. But since x is greater than 1, the right side will now diverge. So the whole sum is actually divergent. Yes, so nothing can be done here. So yeah, these are the kind of mistakes you should watch for. Okay, so yeah, so hopefully you have now understood, got the sense of a proof. Right, so it's a series of mathematical statements. So mathematical statements by definition, they have to be precise. Okay, you cannot use words like I hope or I expect or I believe or I love, right? So avoid using those phrases. It has to be a mathematical statement, every statement, and where every step is derived from the previous one by, so there are so many possibilities which I already mentioned previously, that they may come from axioms or definitions or hypotheses, right? Or so hypotheses are also called premises, or simply a result that somebody else has proved and written down and you have verified. So they are called by many words: lemmas, corollary, fact, proposition, but standard is theorem. Okay, known theorems. So these are kind of the only possibilities if you want to go from a mathematical statement to the next one. Okay, and for the purposes of the course, well, axioms are, you cannot play with them. It will be clear what the axioms are. Definitions will be clear from the context, and hypothesis is what is given to you in the beginning of the problem or the theorem statement. And what theorems you are invoking, that you have to explicitly state. If they are not from the course, if they are external to the course, then you have to prove them in a separate page. Okay, that is what will constitute a full proof. Yeah, just a word on axioms. So like axioms of geometry are given in Euclid's book. They were made explicit in Euclid's Elements. Okay, so what are axioms? I mean, what are the examples of axioms, right? So one is that, I mean, for numbers, you say that 1 plus 1 will be 2 and 2 plus 1 will be 3 and so on. So it simultaneously is a definition for the numbers, but also it tells you about what are the successors, what are the predecessors. For geometry, the axioms are, as expected, pretty trivial, that there is a unique line from any between two given points. Okay, in the Euclidean space, if you are given 2 points, then there is a unique line. Right? There is no way to prove this. I mean, you have to then change the axiom, use some other axiom to prove this axiom, but it won't be interesting because you will always require some other axiom to use this, to prove this. So instead, you can just take this as an axiom and prove other things, not get stuck with this statement, because clearly, all of you believe this. Right? If you don't believe this, raise your hand or talk to me after the class. And similarly, there is a unique circle given center and radius. Right, so these are the two axioms. I forgot whether these are enough, but Yeah, so there are these multiple axioms slash statements which you have to accept, and once you accept them, then you can prove all the theorems of geometry by simple conclusions of this type: axiom, definition, hypothesis, or theorem, known theorem. Okay, so everything else can be proved. In fact, those proofs can also be automated. I mean, this geometry is a kind of simpler mathematical system. So those proofs are kind of, they are, in a way they can be automated. The same cannot be said for other areas of math. For example, if you go to number theory, then already there will be mathematical statements with which you cannot do anything. Okay, you cannot prove them, you cannot disprove them, and so on. So those are more mathematical, those are more complicated mathematical structures, but in geometry, still you can just define, have this list of axioms which are mutually consistent. I mean, they will not lead to a contradiction, and they will imply everything else that is true in geometry. Okay, so that kind of completeness is there. These things can be formalized, but we will not do that in this course. Let's take another simple proof. So let's prove that if n is odd, then n square is odd. Right, so just to exhibit the sequence of statements in the proof, so n is odd means that you can write n as 2k plus 1, right, where k is again an integer. That's the definition of. So this is coming from the premise n is odd. Maybe I should write that. So assume n is odd, that's the premise. And from the premise and the definition, you get some k such that n is 2k plus 1. And what are you being asked? You are asked to study n square. Right? So what is that? N square is 2k plus 1 whole square, which is four k square plus k plus 1, right? And is that odd? Yeah, because it's again of the form 2k prime plus 1. So that means that n square is odd. Okay, so that finishes the proof. But there are some of these implications which are going only in one direction. You can also see that they are reversible, or they are equivalent statements, like this one, right? This also goes backward. So if n is odd, then n is 2k plus 1, but if n is 2k plus 1, it's also odd. So these two are actually equivalent. So we did not have any loss of information. Similarly, the second one, we did not have any loss of information. But yeah, okay. So the last one, where we are saying that if n square is, or where we are saying, say, n square is equal to 2k plus 1 whole square, from there going to n square is odd is clear because of that calculation. But if you want to go backwards, that if n square is odd, then n has to look like that. Is that true? Sorry? No, obviously it's an integer. No, we are not playing games with the definition. Everything is an integer. You can also assume positive integer. But the last implication is can also be made if and only if. It's also an equivalence, but you have to give a short proof for that. Okay, so you may have to fill more lines to show that if n square is odd, then n square has to look like 2k plus 1 whole square. So that again is true. And yeah, so each of our conclusions were actually equivalent statements, right? So it's a very strong proof. Yeah. Yes, so maybe for that I should divide the proof into more steps. I wanted to save time. So this is n square equal to then 2k dash plus 1, and from here we concluded that n square is odd. Yeah, so this is clearly equivalent. If n square is 2k prime plus 1, then n square is odd, and the same thing holds true in the backward direction also. If n square is odd, then n square has to look like that. But the middle implication, what is the problem there? Sorry? So well, that also can be converted, right? That statement has a converse. Is there a problem? But you have to show this, you have to fill in 1 or 2 lines to show that if n square is odd, then n square is actually square of an odd number. That connection you have to show. Sorry? Sorry?
You can do this by contradiction, not the same.
The proof for this this backward implication? Yeah, sure. So you prove it somehow, but let's skip it for now. So the point was that this is a very strong proof because we are going step by step and everything is equivalent. Okay, generally proofs will not be of this type. There will be some loss of information when you go from one statement to the next, because I mean generally what happens is that the theorem itself may not have a converse. Okay, so in that case your sequence of statements, they will slowly become weaker than the previous statement. So you just want to find some proof. You don't want to maintain equivalence amongst all the statements in general. So yeah, so this defines the bidirectional. So note the bidirectional implications. Okay, right, and one more notation. So this premise and conclusion pair we write as P implies Q. Okay, we will use this notation. So there is a premise, which is premise statement, and there is a conclusion statement, and if you can go from one to the next, then we use this implication, forward implication arrow. And we read this as, so read as P implies Q. Okay, where P and Q are mathematical formal statements. So we'll use this P implies Q to mean that sequence of statements are there in the middle which follow from their previous statements, and then taking this path you reach Q starting from P. And the bidirectional one means equivalence. P is equivalent to Q. So then we use this, or denotes equivalence of statements P and Q. And so we, when we are talking about P implies Q, then we say that the converse of this is Q implies P. So this is converse of P implies Q. Now, if you have shown that P implies Q, can you also show the converse? No? Why not?
P could imply Q and R could imply Q.
Mm-hmm.
Like, based on certain conditions, P is true and then that.
But that is very syntactic. Give me an interesting example. Do you know two mathematical statements such that you can move forward but not backward? Yeah, exactly. So just by the definition of that and your experience with squares and rectangles, you can see that if you have defined a concept which is more restrictive than your general concept, then you can always go from general to specific, but you may not go from specific to general, right? So that is what this arrow is quantifying. Okay, it is expressing that you can go from P to Q, so there is some loss of information, and hence you cannot go back. In some cases, you can go back, and then you say that the converse is also true. Okay, so it's a symmetric thing. This Q to P is the converse of P to Q, and P to Q is the converse of Q to P. And when both are true, then you say that they are equivalent. Any questions till now? Hope these things are trivial for you. Okay. Right, so you can check that n is odd if and only if n square is odd. Okay, so okay, this is a short form, but let me define this. So this is if and only if. I mean, basically, okay, let me then write this in words. So P implies Q is also written as, is it P if Q or Q if P? Yeah, so it's Q if P. Right, and the converse is then P if Q. And just to complete the picture, we say that if there is a bidirectional implication, then if and only if, which we shorten to double F. Okay, so these will be our shorthands. Some people don't like this IFF. They force to give the expansion, but here it will be fine. So this if, oh, I should also say only if, right? So where is only if? Yeah, so this you can write as P only if Q. Is that clear? It's simply to confuse you. There are so many terms. They all look very similar. So the mathematical thing is P implies Q. So the symbolic expression is that. So you can say in words as Q if P, or you can say P only if Q. Only if means that if P is true, then it has to be the case that Q is true, right? In English, this is where you will use only if it is consistent with the symbolism. And here it will be what? Q only if P. Okay, so make sure that when you read problems, you don't get confused between if, comma, only if, comma, if and only if. Okay, this is the dictionary you can use to translate. Yeah, you can also say if P then Q. It's the same thing. That's probably the clearest. Is that clear? Any confusion? Yeah, so again, as an exercise, you can write the statement every prime greater than 2 is odd in the above notation. Okay, just think of what should be statement P, what should be statement Q, and then you can put it in this implication by implication or if or only if form. So there are many ways to express the same thing. You have to keep doing these translations. Okay, so now let us, we don't have much time, but start some proof techniques. This was just the definition of proofs. So what are the basic proof techniques or paradigms? So similar to what you do in programming, right? There are these paradigms like recursion or dynamic programming or binary search. So similarly, much before algorithms, there are already similar looking techniques to prove a statement. So first is the easiest one, which is direct proof. That is what we saw when we showed n square is odd, if n is odd. So direct proof is that you start with your premise and then you keep moving forward until you reach the conclusion that you wanted in the theorem statement. So to prove P implies Q, start from P and end in Q. Okay, statement by statement. So yeah, I should not repeat it. It is the same thing that we did with the proof of. We started with n is odd and then statement by statement. In fact, all statements were equivalent in this case, and you reach the end. That's your conclusion. So that is our direct proof. So you can try this again on. All squares are of the form 4k or 4k plus 1. Okay, you can, how do you show this? K is an integer, positive integer. Yeah, so you start with that 2k or 2k plus 1, then you square it and you get to this place. 2k will give you, I mean, let's say 2k prime square, that will give you 4k, and 2k prime plus 1 square will give you 4k prime plus 1. That is what actually we deduced. Right? So actually we deduced a stronger thing in that starting from n is odd, we actually got to 4k prime plus 1. So that is what we have shown directly. Now indirect proof will be, well, where you don't start with p, you start with something else, but still get to q. This is not really a technique. We'll divide indirect proofs into many cases, but indirect proof example will be in the version here will just be if you had to show that numbers of the form 4k plus 2 or 4k plus 3 are not squares. Right, so here if you took the direct approach, then you will be screwed because you have to somehow show that if 4k plus 3 is equal to n square, then there is no n. Right, so that seems pretty hard to show. How do you show that for any k, any positive integer k, the square root operator on 4k plus 3 is not an integer? Right, that's pretty hard. So this is why how you start and proceed, you have to be very creative. So instead you look at you study squares and not squares. Right, so you study squares and there you deduce 4k plus 1. And then from there you indirectly conclude that everything else is not a square. So that's 4k plus 2 and 4k plus 3. Which is kind of again a proof by contradiction. Right? It's an indirect proof. So your choice of the proof method is very important because otherwise a proof may not even exist if you start with a bad technique. Okay. So what are the indirect proofs? So first is contrapositive proof. Have you heard this term? What is that? Yeah, so to show P implies Q, you assume negation Q and get to negation P. Right? So we write it like this. So to prove P implies Q, what you do is start from negation Q. Okay, this will be our notation for negation of Q or not Q. Okay, so negation or not Q, start from this and deduce or conclude with P or negation P? Yeah, conclude with negation P. And somehow that magically means that P implies Q. Right, so this is, can compare it with arithmetic. It's like you brought Q on the left side with a minus sign and you sent P to the right side with a minus sign. Right, so these two things are actually equivalent. You can show this as a simple example, as a simple exercise. So convince yourself that if I show P implies Q, then I have shown that negation Q implies negation P. And if I have shown that negation Q implies negation P, then I have shown P implies Q. Okay, that's the contrapositive proof starting point. Okay, let's just do an example for this and stop. So we want to show that if n greater than 3, so let me use the implication. If n greater than 3 is prime, then n plus 1 is not a square. Okay, so first thing is P, the second is Q. And you want to show P implies Q. How do you show this? Essentially, you are showing that primes are not square minus 1, right? But you don't have a formula for prime. So how do you in general study prime minus 1? So here, the only way you can prove this is by an indirect proof, and in particular by a contrapositive proof. You can give a contrapositive proof. You assume that n plus 1 is a square. Okay? Then what? Exactly. So that's the contrapositive proof that if you start with n plus 1 equal to a square, let's say x square, then what happens? N is x square minus 1, which is known to be, its factors. Right, so this is a streak of luck that strikes. So now you actually have a factor of n. You can factorize n, right? Except in the case, yeah, so if x minus 1 is 1, then this is not a factorization. But then you see that n is what happens when x is 2? In that case, n is 3, right? So we have ruled n equal to 3 out because we are assuming that n is greater than 3. So in those cases, by hypothesis, this means that n is composite. Right, so negation Q implies negation P. That's what you have shown. So which means that P implies Q is what you have shown. Is that clear? That's a contrapositive proof. Exercise is, can you do this directly? Right, can you start with prime and then understand primes enough so that n plus 1 you can show is non-square, not a perfect square? Seems pretty hard, but this is a very simple proof. So yeah, every time you will see in this course, especially in the exams, that where you start, some creativity will be needed. Okay, how you start. Generally, just the direct approach, you will try, but it will not work. Is there anything else? Yeah, so okay, let's give a warning. With this proof paradigm, so what about if you show to show, as always, P implies Q, you show negation P implies negation Q. Will that finish your proof? Why not? Yeah, because this is actually you are showing Q implies P. Right, so if you show Q implies P, it may not mean in general that P implies Q. Right, so you are actually showing the converse and you are not showing the question that was asked. And this will generally give you 0 marks if you do this, because the converse may be very easy. Then you show the converse. Then you only show P implies Q. Okay, so you are showing something related to P implies Q, but it's not P implies Q, it's actually Q implies P that you are showing. So in the case when converses are easy, this will not mean much. But yeah, if you are asked to show equivalence of P and Q, then this is kind of half of the proof. So there is a difference again how you start. If you start wrong, then if you start with negation P, then you are not getting anywhere. If you start with negation Q, then you get somewhere. Okay, so then